Assalamu alaikum. Let's begin lecture 18 of CS 218 Data Structures and Algorithms. Our topic is recursion, for which we are using chapter 10 of book 1. In the last lecture, we implemented the iterative and recursive versions of the factorial function. We looked at two recursive functions for printing values. We implemented the iterative and recursive versions of the function to find the nth term of the Fibonacci sequence. We implemented a better function to find the nth term of the Fibonacci sequence. And we found time and space complexities of all codes. Tail recursion. Tail recursion is the situation in which, when the base case is reached, there is no value to return to the calling function, and only a simple transfer of control takes place. As an example, consider this code. Print list node is a recursive function. If node is not none, it prints node.data and then it calls print list for node.next. Let me show you how this function works. This function is actually working with a linked list. So we have a linked list and one of the nodes in the list is being pointed to by node. This is the argument that we provide to the print list function. I call print list node. So I give the print list function pointer to the node containing D. Inside the body of the function, it checks if node is not none and node is not none. So it prints node.data. The node to which this pointer points contains D. So D is printed. And then this function calls print list for node.next. Node.next is the pointer in the node containing D. So when the next instance of the function is called, the argument to this function, the function in pink, is pointer to the next node. Now, this function checks if the pointer it is given is not none, and it is not none. So it prints the data of this node, which is B. And then it calls the print list function for the pointer inside this node. So when the next instance is called, the instance in blue, the node pointer is none. Now for the instance in blue, node is none. Since node is none, the if is false and its body cannot execute. Actually, the last instance has no statements to execute, so it transfers control to the print list function that called it. Now, the print list function in pink had left off execution at the very last line. When control transfers back to it, it does not have any more lines to execute. So it transfers control to the function that called it. And the same thing happens to the print list function in purple, and it transfers control to me. In tail recursion, we use a stack even when we do not need it, which leads to a higher space complexity. We are going into recursion and saving items on the runtime stack, but we don't have anything to do in the body of the function. So when control transfers back to the function, it also simply transfers control back to the function that called it. If tail recursion is identified in a code fragment, it should be replaced with iterative code that does the same thing. So now that we have identified that the code in yellow has tail recursion, why not try to write an iterative version of this code? Look at the new code here. Define print list node. A is node. If A is not none, print A dot data and advance A. In the recursive functions we have seen so far, identify those that use tail recursion and write their iterative equivalents. Now we come to a very interesting topic, Tower of Hanoi. The Tower of Hanoi, also called the Tower of Brahma or the Lucas Tower, was invented by a French mathematician, Edward Lucas, in the 19th century. At the beginning of the universe, in a Hindu temple in Benares, the young priests were given 64 gold discs stacked neatly on one of three diamond posts. Each disc rested on a slightly larger disc. The priest's goal is to recreate the stack on a different post by moving discs one at a time to another post, with the rule that a larger disc could never be placed on top of a smaller disc. It is said that before the priests complete their task, the temple will crumble into dust and the world will vanish in a clap of thunder. The rules for the puzzle are only two. 1. A larger disk can never be placed on top of a smaller disk. 2. Only one disk can be moved at a time. So how to play the game with just one disk? A is the peg on which the disk is stacked. This is the source peg. B is the auxiliary or helping peg. C is the destination peg. But with one disk, we don't require a helping peg. Move disks from A to C. Done. The puzzle is solved. Total moves is 1. How do we play the game with two disks? A is the peg on which the disks are stacked, the source peg. B is the auxiliary or helping peg. C is the destination peg. The first move is to move disk from A to B. The smaller blue disk is moved to B. Then we move disk from A to C. The larger red disk is moved from A to C. Then we move the disk from B to C. The blue disk that we earlier placed on B has now been transferred to C. Total moves is 3. How do we play the game with 3 disks? A is the peg on which the disks are stacked, the source peg. B is the auxiliary or helping peg. C is the destination peg. Write the moves. They are in front of you. total number of moves is equal to 7. So why are we interested in the towers of Hanoi? We want to write a piece of code that prints out the correct sequence of moves for Tower of Hanoi for n disks. The solution must not list more moves than necessary. This puzzle is a good example of problems that can only be solved using recursion. Steps of solution. Step 1. Move the top n-1 disks from A to B. Step 2. Move one disk from A to C. Step 3. Move n-1 disks that you just placed on B in step 1 to peg C. Recursive code for Tower of Hanoi. Here I am going to use the 3 steps that I just showed you. The name of the function is TOH. It takes 4 arguments. Num is the number of disks. First is the name of the source peg. Middle is the name of the auxiliary peg. Last is the name of the destination peg. First we check that the number of disks given to us is greater than 0. If there is only one disk, then the move is simple. Actually, one disk is the base case for this recursion. So for one disk, we simply say move the disk from the first peg to the last peg, and then we return. But if we have more than one disks, then we call the function 3 times. We had a look at binary recursion when we were working with Fibonacci. Here, we are not calling a function twice within itself. We are calling a function 3 times within itself. First, we call TOH for num-1 and we ask it to take them from the first peg to the middle peg. Whatever peg is remaining, that becomes the helping peg and that is placed in the middle. So in the third last line, I have written TOH num-1. First, this is the source. Last, this is the helping. Middle, this is the destination. Then in the second last line, I have written TOH1, first, middle, last. I am trying to say move one disk from the first peg to the last peg. This is actually step 2. The last line of the code says TOH num-1 middle, first, last. Now here middle is the source peg, first is the helping peg, last is the destination peg. This line is saying take n-1 disks from the middle peg and take them to the last peg. This is an implementation of the steps that we saw in the previous slide. Does this code work? Let's see. The code is in front of you and I am going to trace through it for 3 disks. My initial call is TOH3 ABC. What am I trying to say? There are 3 disks. They are on peg A. Take them to C. 3 is not equal to 1. So this function is going to generate 3 recursive calls. The first of them is this. TOH to ACB. In the first step, we take the upper n-1 disks from the source peg to the auxiliary peg. Look at the pink box. The auxiliary peg is B. So in the green box, we have asked to take two disks from A to B. In this green box, 2 is not equal to 1. So again, this function will generate three recursive calls. The first of which will be this. TOH1 ABC. In the green box, the source is A, the destination is B, and the auxiliary peg is C. So the first recursive call generated by the green box wants to take one disk from A to the auxiliary peg C. In the orange box, num is equal to 1. This will translate into a move. The move is from A to C. And then the function instance, that is orange, will return to the function instance which is green. The first recursive call is complete. The green function instance will generate the second recursive call, TOH1 ACB. Take one disk from the source to the destination. Look at the green box again. The source is A, the destination is B. And that is the same source and destination in the second orange box. The second orange box translates into another move. Move a disk from A to B. Two recursive calls of the green box are complete. So the green function instance generates the third recursive call, TOH1 CAB. Here we are executing step 3. Previously, in step 1, we had placed a disk on peg C. Look at the topmost orange box. Now we are going to take that disk from peg C to our destination, peg B. Who determines the destination? The calling function. The calling function is green, and you can see the destination there is B. TOH1CAB, the third box, generates a move from C to B. All recursive calls of the green box are now complete. So it returns to the pink function instance. And the pink function instance generates its second recursive call, TOH1 ABC. Take one disk from the source to the destination. Now this can translate to a move. A goes to C. Now two function calls are complete for the pink function instance. This function instance will generate its third recursive call. In the first green box, we had taken two disks from A to B. In the bottom green box, we are picking up those two disks from B and taking them to the original destination C. Who determines the original destination? The pink function instance. So the bottom green box says take two disks from peg B and place them at C. Now since num is not equal to 1, the bottom green box will generate three recursive calls. The first one is this, TOH1 BCA. In the first step, we take n minus 1 disks from the source to the auxiliary peg. Look at the bottom green box. The auxiliary peg is A and the source is B. So in the first recursive call generated by the bottom green box, we are taking one disk from B to A. This will generate into a move B to A. The first recursive call is complete. The bottom green box makes the second recursive call. TOH1 BAC. The second recursive call has the same last three arguments as the last three arguments of the calling function. So the second recursive call generates a move B to C. Two calls of the bottom green function are complete. It makes its third recursive call. Now it is taking the disk that it placed on peg A in step 1 and it is now placing it at the original destination. Again, the bottom green box will give you the original destination C. So the last orange box says TOH1 ABC. Take a disk from A to C. And this generates into a move A to C. Now, all recursive calls of the bottom green box are complete. So it returns to the calling function, the pink function instance. All recursive calls of the pink function instance are complete. So it returns control to the calling entity, which is me. How do I read the moves of Tower of Hanoi? I read them like this, from top to bottom. These are 7 moves, and if I go by these moves, I can play the Tower of Hanoi puzzle for 3 disks. Here is a task for you. Make a tree of recursive calls for Tower of Hanoi with 4 disks. An advice is to draw in landscape orientation because you will need space to draw. Take a snapshot, save it as my roll number leg 18 and submit your response in the assignment titled Lecture 18 Tasks in Google Classroom. How much time does it take to play the Tower of Hanoi? Let Tn be the number of moves required to take n disks from one peg to another. Then Tn minus 1 is the number of moves required to take n minus 1 disks from one peg to another. Now, number of moves required to take n disks from one peg to another is number of moves required to take n minus 1 disks from source peg to auxiliary peg. This is step 1. Plus number of moves required to take one disk from source peg to destination peg. This is step 2. Plus number of moves required to take n minus 1 disks from auxiliary peg to destination peg. This is step 3. So Tn is Tn minus 1 plus 1 plus Tn minus 1. The first term is number of moves for step 1. The second term is number of moves for step 2. And the third term is number of moves for step 3. So we rewrite it as this. Tn is 2 Tn minus 1 plus 1, and T1 is 1. This is the base case. When you have one disk, you need only one move. We solve the recurrence relation using backtracking. Tn is 2 Tn minus 1 plus 1. Look at Tn minus 1. I will substitute it with its recursive definition. Tn minus 1 can be written as 2Tn minus 2 plus 1. Now Tn is 2 raised to the power 2, Tn minus 2 plus 2 plus 1. Again concentrate on Tn minus 2. I substitute it with its recursive definition. Tn minus 2 can be written as 2Tn minus 3 plus 1, and Tn becomes 2 raised to the power 3 Tn minus 3 plus 4 plus 2 plus 1. Look at the first equation. Tn is 2 to the power 1 Tn minus 1 plus 2 to the power 0. The power of 2 in the second term is 1 less the power of 2 in the first term. Look at the second equation. Tn is 2 to the power 2 Tn minus 2 plus 2 to the power 1 plus 2 to the power 0. Again the same thing. The power of 2 in the second term is 1 less the power of 2 in the first term. Look at the third equation. Tn is 2 to the power 3 Tn minus 3 plus 4 plus 2 plus 1. Again the same thing. Power of 2 in the second term is 1 less power of 2 in the first term. Generalizing, we write for k. Tn is 2 to the power k, Tn minus k, plus 2 to the power k minus 1, all the way to 2 to the power 1, plus 2 to the power 0. The box encloses a finite decreasing geometric series. Do you remember the summation formula? Sum of a finite decreasing geometric series is A in brackets 1 minus r raised to n whole divided by 1 minus r. A is the first term, r is the ratio, n is the number of terms. How many terms are here? From k minus 1 to 0, there are k terms. What is A? 2 to the power k minus 1. What is the ratio? 1 upon 2. Putting all these things in the formula for summation of a finite decreasing geometric series, I get this. Summation of k terms. 2 to raised to the power k minus 1, brackets 1 minus 1 upon 2, this is the ratio, raised to k, whole divided by 1 minus 1 upon 2. When you simplify this, you find that the summation is 2 to the power k minus 1. This summation can replace everything that you see in the green box. So substituting the sum in the recurrence relation, Tn is 2 raised to k Tn minus k plus 2 to the power k minus 1. Now look at Tn minus k. I want to be able to place the base case here. The base case is T1 equals 1. If n minus k equals 1, then k is n minus 1. So putting k equals to n minus 1, Tn is 2 raised to the power n minus 1, Tn minus n minus 1 plus 2 raised to the power n minus 1 minus 1. So everything in the bracket of t becomes equal to 1, which we can substitute by 1. And we are left with this equation. Tn is 2 to the power n minus 1 plus 2 to the power n minus 1 minus 1. 2 to the power n minus 1 is written 2 times. I can write it like this. Tn is 2 times 2 to the power n minus 1 minus 1. And then I write this. Tn is 2 to the power n minus 1. This is the number of moves required to play the Tower of Hanoi for n discs. Since this is the number of moves, this is also an estimate of the time taken to play the Tower of Hanoi for n discs. And from this equation, I can say that the time complexity to solve the Tower of Hanoi is O2 to the power n. Investigating the truth of the legend associated with the puzzle. If the priests do not take any breaks to eat, sleep, or go to the bathroom, and move the discs at the rate of 1 disc per second, mind you, this is a very fast rate considering that they are working like angels. They are not taking any human breaks. Then they need 2 to the power 64 minus 1 seconds. So let us convert the unit so that it becomes easier for us to understand. Divide this by 60. This becomes minute. Divide this by 60. This becomes hours. Divide this by 24. This turns into days. Divide this by 365. This turns into years. So they need this many years to finish the game. Ancient light from the Big Bang has revealed a precise new estimate for the universe's age. The universe is currently 13.77 billion years old. How much time does the priest's game take? Do you think the story is mathematically believable? So what did we learn today? We were introduced to tail recursion. We learned about the legend related to the puzzle of the Tower of Hanoi. We generated the set of moves for Tower of Hanoi when played with 3 discs. We found a formula to determine the number of moves to solve the Tower of Hanoi problem. You have to read the book, submit your answers to the tasks in this lecture, note your questions and put them up in the relevant online session, and email your suggestions to me if you have any. Take care. Allah Hafiz.